Hello everyone, this is Kanwarpal Singh Mehra. This is my project one for computer vision class. Here my topic of project is to use computer vision to recognize food on the plate. So basically the problem is like to assist some blind people to detect the food what they are going to intake from the dining plate. Sometimes like when the food is served to a large number of people, especially when blinds are served the food. So they never know exactly what they got in their plate. They can smell, but still, it is not as good as we other humans can see that what we are going to eat. So the approach of this app is to to tell the blind people that that if they take the picture of their dining table so that they can detect in that image that they may going to eat this food, this fruit, or these vegetables and all. This is the abstract of my application. Basically we are not doing any computation on a mobile device. We are using a mobile device just to take the pictures of your table, and then we're gonna do all the processing on the back end and send the response, the classification response, back to your mobile device, to your activity, telling that the classified food could be of this type. uh, this problem is basically uh, this basically I'm dividing this problem here in two major parts. uh, like firstly we need to detect that which portion of the dining table may contain some food. There could be many objects, many unwanted things like clothes, like tissues and all, but the food could be present only in some like dining plates or some other sort of vessels. So basically, in this, as per the scope of this application, I'm limiting my research to detect a particular type of dining plates, the round plates I have chosen in this tutorial. So we're gonna study a well-defined approach how to detect a round circular dining plate from a dining table, and then we have a well-defined algorithm, a structured algorithm to detect the food further in that plate. Detection of food has been accomplished like in three basic steps. Firstly, we are segmenting the whole image pixel, like we are differentiating due to some properties that this could be a different food, this could be a different food. So basically we are segmenting the pixels in the first place. Then we are trying to extract out some features from those pixels. We are fetching out some of the properties that each pixel represent. Then using those properties we're gonna match each pixel, or we're gonna do some clustering on the pixels that uh, that that so many pixels can collectively represent a particular type of food only. So then in the final phase, mm, what we are doing is we are comparing our image with our from a with an image from our trained data set, and using a confidence score we are assigning a particular class to our captured image that these this type of foods are present in the plate as per the picture taken. So going into little more details about the plate detection. So here, as I told earlier, that we are focusing only on the round circular plates only. So when we take the image of the table, then we can have easily the edge map of the pixels. But here, as we are limiting our approach to round plates, then we are using here a predefined algorithm to draw the curves and split those curves at some few specified points. There are many available algorithms for line drawing, so we can draw each and every curve there, and we can split those curves at three well-defined points. So let's say no, it is quite obvious that our images are in 2D plane. So every arc, every line, every structure in a 2D plane can be represented using two variables at max. So any curve can be represented as y is equal to some function of x. So we are using this property. We are using mathematical properties of differentiation. So basically, do the first differentiation of y with respect to x, and we choose two critical points here. The first one is where the first differential of this function is defined, and that is equal to 0. And the other one is where uh, the tangent, where the first derivative value is not defined. So these are basically the 2 points where when we draw a tangent to any curve, so either it could be just at the 90-degree to the x-axis, that it is along the vertical axis, and the other option is when the tangent line is parallel to the horizontal axis. The third point is we are considering here is where the second derivative of the function is equal to 0. So at these three critical points, basically we are splitting each arc, and then and then we are trying to do optimal arc filtering here. What does this mean? Optical arc filtering means here we are trying to just focus on the some possible arcs which can form around circular plates. So here we are eliminating all the other arcs which are coming from some unwanted objects. With the basic criteria which has been assumed in this algorithm is that the arcs which are coming from the clutter, like other than plate stuff, so they are kind of more irregular, and the arcs which we are getting from a round circular plate is is more regular, is having more elliptical contours. So in this way we are just picking uh, the arcs with a regular elliptical contours, and then we are trying to converge those segments of arc to form a circular plate. We are here we are using the basic property of convex objects. So like uh, if we have an arc, then if we select the midpoint of that arc and we draw a tangent to that arc, and from tangent we draw a line at 90-degree. I can show you in the tutorial as well what I'm talking about. Let's go to this image first. This is what I'm talking. So this is an arc, and this is a tangent drawn, and this is a line. So it is the property of uh, like convex objects. Concavity is the important feature that it tells us that the if we want to join all the missing edges of this arc which can construct a round plate, so we will definitely found all the objects in this part. So the whole object will lie in this part of the image, which is the darker the shaded region of this image. So we are eliminating the rest of the portion of the image, and we are trying to focus where we can find the other connecting parts of an arc. So this way we group the several arcs, so we can have several elliptical contours, and then ellipse identification is done, like we are using some sort of confidence score, and which is matching best to our possible construction, and this way we detect a plate. This is the first step. In the overall step, here we are using like some sort of functions for the optimal arc filtering, as I earlier told. So it is just it is just a function of the variance of the plate and clutters. So as clutters could be more varied, they have more irregular structures. So we are using arg minimum function. Arg minimum function is nothing but taking the values where a function could have minimum values. So in this way, our first target is achieved, that we are detecting a plate here, and then our focus comes on food detection. Food detection, as I told, it is again a part of three subparts, sub tasks: the multiple hypothesis segmentation, the feature detection, and the classification. In multiple hypothesis segmentation, we basically do three segmentations. Salient region detection. Salient region detection from the whole table is nothing but the plate detection, which we have discussed earlier, and I have created a special and I have represented a special algorithm to do this part. So salient region detection is done as the dining plate detection. Then we have multi-scale segmentation. In multi-scale segmentation, now we have detected the plate. We have reached to some part of the plate where a food items could be present. So on that particular portion of the image, we are doing multi-scale segmentations. We are trying to extract that what are the different varieties of food, or the different possible classes of food are present on one plate. I will explain this step in detail when I go to the website again. And the third part is fast rejection. Here in the plate, when we do the segmentation, here we don't want to waste much of our processing towards doing each and every computation towards some undesired pixels. Like here, when we do the segmentation, then we assign a specific threshold. We use a threshold that if certain pixels are not crossing that threshold, then we drop them immediately. We classify those pixels as part of the background. So this makes our processing a little bit faster. So let me go to the multi-scale segmentation on the website. This is salient region detection. This is nothing but the plate detection here. Basically, the generalized approach for every salient region detection is like generate a foreground and a background image by labeling these color spaces. So present strong edges as RGB channels of image and use skinny edges to estimate the edges. Again, we got the edges. Now we're gonna use those edges. We're gonna divide those arcs, and as we have limited our approach to round plates, so we're gonna optimally filter those arcs, and then we're gonna combine those arcs, and using the Euclidean distance between normalized edges of the histogram, we ultimately found what is the salient region for detection. In the multi-scale segmentation, multi-scale segmentation, our target is to like cover both the coarse and fine level details from the image. In this we use cuts, and our whole image has been like transformed into a undirected graph where each pixel represents the node of that graph, and these pixels are disjoint in itself, but they are connected to each other with the edges of the graph, and each edge of the graph represents some sort of weight. That weight is nothing but that is the measure of the affinity, that is of, or the similarity between the two pixels. Like from a picture of one type of food, let's say a fruit apple. So we are getting 2 pixels from the apple, and the 2 pixels are supposed to have maximum affinity. So the weight on that edge will be maximum because it belongs to the same object. So in this way, we are having we got some defined formulas uh, formulas to calculate the weight on each edge. The this formula is calculating the weight on I and jth pixel, where I and ij are the pixel intensities and xi xj are the locations. So this formula pretty much gives us the weight on edge. And here's another method where we use the edge value here, combining these two methods with some tuning parameter alpha. We got a combined weight on ith and jth pixels. In this way, we have structured the whole image into undirected graph, each pixel representing a node, and the two pixels are joined by, which are actually the disjoint pixels, but they are joined by the edge in a graph, and that edge contains some sort of weight. So here basically we are combining all these weights, and we are doing a W reconstruct, which is we are representing the whole image again, where we have shown the varied ranges of spatial separations, like where wi w2 belongs to some like fine finely defined, like very spatially close pixels, and then we include the uh, representation of some much varied pixels. So in this way we get the whole content, the whole pixel information, but in a more compressed way. uh, this is the fast rejection, as I told earlier. So in this approach they use a threshold of 500. So we remove all the smaller segments than this and regard them as background of the image. The next step in food detection is the feature detection. uh, as we talk about the computer vision, how the human eyes are detecting some sort of objects. Like if we talk about how we humans detect some sort of objects, firstly we look at the color of the object, that what color object it is, and then we may like judge it by its structure, its size, that what is the size, how it's structured. And the third thing, if we have the same size and same color, then we may further discriminate using some sort of texture. So here in the feature detection of the food, we are using well the color features and the texture features, but we are not using the size features here because we have already done the segmentation in the first step, and this does not uh, let us with the already defined there the properties of this size, because we have done segmentation to the pixel level, so we cannot classify the objects using the size of object. In global features, uh, in global basically we have like two type of features: the global features and the local features. Global features are the features of the whole image, where we are taking the whole image of the plate and we are reading each and every pixel present in that image. In the local features we are targeting upon some specific key points only, that which mostly are believed, which are mostly potential points that may contain food. So we collect 6 local features and 6 global features. In the global features we have two type of features: the global color features and global texture features. Let me go to the website, I can explain each and every one there. This is the global color features. It consists of like 3 different color statistics: the global color statistics, entropy color statistics, and predominant color statistics. The global color statistics is consists of first and second momentum of statistics of these color spaces, and one feature vector for the entire image segment containing the two moments of each color component is obtained. So basically we are getting the values for each of these color spaces, but for the whole image we are just getting our output from this step is the one uh, color feature vector. And the second is entropy color statistics. It is it is there to give us the distinctiveness and repeatability of a color information for each color space component using entropy. We are calculating entropy on each and every pixel. Again, it is the estimation of first and second moment of statistics of the entropy in RGB space component. Predominant color statistics is here, which tells us that which color has the predominance in the whole image. But again, just one feature vector for this predominant color statistics is obtained. So we got total three feature vectors from global color features. And now I'm talking about global texture features. In global texture features, again we got three feature vectors here. The first one is gradient orientation spatial dependence matrix. The gradient is somewhat like the surface of the food. So basically, we are trying to study the how the surface is oriented, like whether it is just flat, parallel to the base, or it is little bit upward. So this way, we are trying to detect some sort of texture features here. Basically, we try to extract four different values, four different statistic features like correlation, angular, second momentum ASM, entropy, contrast, and homogeneity. But we are getting these five values at four defined angle positions, at four different angular orientations. uh, these four angular orientations are 0, 45, 90, and 135 degrees. So after these measurements, we make one feature vector for the entire texture region, and which is which is basically a spatial dependence matrix. It is a spatial dependence matrix, and it is defined for each distance like fd1. It goes as 2 raised to power 0, 2 raised to power 2, 2 raised to power 4, in this way. So for each of these fdi, we define a complete matrix at all the four angles for all the five values, and this collectively make gives us the one feature vector, the one GOSTM feature vector. The entropy categorization and fractal dimension estimation is the second feature vector here. So basically, it is based on multifractal analysis. Each pixel, for each pixel, we are calculating the entropy. Entropy is the like information of pixels, and we are comparing those entropy values. We are trying to find out which two or more pixels have the same entropy, and we are doing clustering on those pixels, so that they may represent a single type of food. This gives us the one feature vector for the whole information. And we have another one, Gabor based image decomposition and fractal dimension estimation, called GFD. In this, basically, we use Gabor filter banks, and we use fractal dimension. Fractal dimension used in these two feature vectors. It is like when we scale up an image, so how the edge is gonna change. So basically, like if we talk about any general image, let's talk about the map, the word map. So we can see a typical structure of an continent. Then we zoom further and further and further, then our edges are getting more defined. So it is the calculation of those edges, which can give us some idea of the texture of the food. So as for now, we got three color feature vectors and three texture feature vectors, and now we're gonna have the local feature vectors. Local feature vectors, as I mentioned, they are focusing on some key points only that could potentially have the food. So there we have SIFT detectors, surf detectors, and we have the shift detectors on each R and GB component. So in total, we have 12 feature vectors here, and uh, now the next step in our approach is the classification. In classification, we are having the segmented region SQ and input image IQ and a feature vector FQ. We are comparing initially at individual level each feature vector. Uh, Let me go to this image. Let me zoom it. So this is our image. We do segmentation. We extract the features. We extract global features, local features. In our training data set, we have the same thing. We are extracting global feature channels and local feature channels. Uh, what we are doing here, we are comparing in each and every feature vector individually, and we are getting some sort of result out of here. And each result points out a pixel to some sort of class based on our training data set, and after that we combine all those results to give us the final results of the classification. So if we are here, it is like a iterative method. So if we see any sort of improvement here that uh, it is not crossing our predefined threshold value or our confidence score, so we can try again to extract some sort of features and try to rematch all these feature vectors with the trained data sets feature vectors in order to get at least some predefined confidence score. And then once that is achieved, we got our output, that is sent back to our uh, Android device. So basically in this tutorial, this is the brief introduction which we have discussed in details. So in the system architecture, we have hardware. We just need a Android device which is equipped with a camera. The rest of the thing, we I'm not like specifying on its architecture because every device can take the images, and the connectivity to the internet allows us to get the data to our backend when we are doing all the processes on the backend. So it's pretty much straightforward that we just need a mobile device, a Android device, which is equipped with the camera. Algorithms we have discussed so far in details. Success and failures. The success of this project is conditional. It largely depends upon which type of food we are capturing. Like uh, some foods in India, which are well cooked, so they get so much fused into like 10 15 ingredients that we cannot detect them neither from their color or from their texture that what are the ingredients in that food. So it depends on it is conditional, like it depends what type of food we are trying to detect. If in a plate we just have an apple and a banana, so it is like uh, the best case, it can detect it very easily. uh, the challenges which I assume that could be part of this tutorial, like the robustness of this app depends upon the training set as well. It is again a concern of how we have trained ourselves, how we have done our homework, that how well equipped our data set is. The confidence score is set to some arbitrary value that the segmented feature vectors surpassing each threshold would qualify to be classified. So basically, deciding such values of thresholds is also a very deciding factor to decide a very accurate value for those thresholds. Infrastructural perspectives, from infrastructural perspectives, the quality of image matters. Like some devices could be equipped with very good quality of lens and more number of pixels. That makes our work like more computationally powerful, because we are getting some good information from the captured image. While if the picture in itself is very bad, the lens is not very clear, so the information which we can extract from our captured image is not that much rich. So these are the challenges which I assume one can face while implementing this algorithm. Uh, this conclusion and the future work. The future work here, I assume that we can use this app to classify food, and then we can use this app as an application towards detecting the caloric value of the food. Like some health conscious people, they just want to know how much calories they are intaking in a particular meal. So for those people, it could be a very useful app which can detect your food and then use some sort of trained data sets and tell you back that you are consuming this much of calories. This is the next level approach. The bibliography here, I used two papers basically. The first one is defining very clear the approach to detect round plates, and the third one is going over segmentation, classification. No, the segmentation, the feature detection, and the classification. So that's it. Thank you so much.